Right, a bit more of an investigation about the roots of a quadratic. We touched on this idea earlier when it came to forming quadratics, but if alpha and beta are the solutions of the equation, the roots, the x-intercepts, call them whatever you like, but think of them as roots because they may not exist, remember, they might be imaginary, but there's always going to be two. Sometimes they're the same, sometimes they're different, sometimes they're imaginary, but there's always two. So we'll call them alpha and beta. Well, what I know is I could then factorise this quadratic to be a outside of x minus alpha x minus beta. That would give me solutions alpha and beta. So I just expand that right-hand side out, do a little bit of grouping, divide both sides by a, then I come up with the relationship that I need. The sum of the roots is always minus b on a. The product of the roots is c on a. And again, it comes back to that idea when we're solving quadratics. We say, what adds together to give the middle term? What multiplies together to give the last term? But normally with those sort of questions, it's a monic. So A is 1. And so that's why we say, what adds together to B and so on. So there's sum of the roots and the product of the roots. Now we can have lots of fun playing with the relationships of the roots. So first one, we looked at questions like this before. If they say form a quadratic equation whose roots are, well, we can always work out the sum in this case. Now, whether you write it down or not, of course, is another matter. But, sum's minus 1, product's minus 6. So the quadratic must be x squared plus x minus 6. So it's going to be minus the sum plus the product. The advantage of ones like this, because remember, they will always be in conjugate pairs. And the advantage of that is when we add conjugates, will be 4. Alpha beta turns out to be difference of two squares, 4 minus 5 minus 1. And so there's my equation. X minus the sum, so minus 4, plus the product, minus 1. But we can have more fun than that. Oh, yeah. Here's our quadratic. 2x squared minus 3x minus 1 equals 0. Sure, we could go and find alpha and beta, but that's no fun. We're going to find out what alpha plus beta is without actually finding alpha and beta. 3 on 2. Alpha beta? Minus a half. Alpha squared plus beta squared. And I've boxed that result because it's good. It comes up a lot. It's such a common question they love to ask. Alpha squared plus beta squared. Basically, it's just your expansion rearranged. So your perfect square rearranged. And we've worked out what alpha plus beta is, and we've worked out what alpha beta is, so sub it in, and 13 on 4. Another common question they like to ask is the reciprocal of the roots added together. Yeah, it becomes like an algebraic fraction question. Common denominator becomes the product of the roots, and then the numerator becomes the sum of the roots. And in this case, well, the 2's will cancel, minus 3. We're going to find the value of m if one root is double the other. So in this case, instead of calling the roots alpha and beta, I'll call them alpha and 2 alpha. One root's double the other. So alpha plus 2 alpha is negative 6. And alpha times 2 alpha is m, and that's what we're trying to find. So basically, we've just got simultaneous equations to work it out. So alpha is negative 2, summing it in, eventually we get an answer. There it is, 8. Find the value of m in this wonderful equation, 2m minus 1x squared, 1 plus mx plus 1. One root is the reciprocal of the other. So instead of calling them alpha and beta, alpha and 1 on alpha. But the beauty of that is the product of the roots. I don't actually need to know what alpha is. Product of the roots is always going to be 1. So in this case, alpha times 1 on alpha is 1 on 2m minus 1. Yeah, m turns out to be 1. In fact, the middle term there, 1 plus m, I didn't really need. Had nothing to do with it in this question. There we go. Exercise 8H.